Hello! In this video, we are going to prove the following theorem. Let a be a real number. Then for all non-negative integers m and n, a to the power of m times a to the power of n is equal to a to the power of m plus n. Now, our definition of non-negative integer exponents will be as follows. Let a be a real number. For each non-negative integer n, we define the real number a to the power of n recursively as follows. So a to the power of 0 is going to be equal to 1. And then for each non-negative integer n, a to the power of n plus 1 will be equal to a to the power of n times a. So now, let's get into proving this theorem. So the way we're going to prove this is we are going to start by giving ourselves an arbitrary non-negative integer m. From there, we are going to proceed by induction on n to show for all non-negative integers n, a to the power of m times a to the power of n is equal to a to the power of m plus n. So let's start with the base case. In the base case, we're trying to show that this equality is true in the case where n is equal to 0. So we're trying to show that a to the power of m times a to the power of 0 is equal to a to the power of m plus 0. So let's write out the left-hand side. Now, we know, according to the first part of the definition, a to the power of 0 is just 1. So this is just a to the power of m times 1, and any real number times 1 is just going to be that real number. And then we can take the m, replace it with m plus 0, right? Because m is equal to m plus 0. And so we're done. We see that a to the power of m times a to the power of 0 is equal to a to the power of m plus 0. So we have shown that this equality is true in the case where n is equal to 0. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary non-negative integer n, and we assume that this is true. And from here, the whole goal of the induction step is to show that this equality is also true for n plus 1. So we want to show that a to the power of m times a to the power of n plus 1 is equal to a to the power of m plus n plus 1. So let's write out the left-hand side, where instead of n we have n plus 1. Well, according to the second part of the definition, a to the power of n plus 1 is just a to the power of n times a. Then by the associative law, we can move these parentheses around a to the power of m times a to the power of n. But we know that a to the power of m times a to the power of n is equal to a to the power of m plus n, according to our induction hypothesis. So we have a to the power of m plus n times a. But now we're in a position to apply the second part of our definition again. Applying the second part again, we have that a to the power of m plus n times a is equal to a to the power of m plus n plus 1. But then we just move these parentheses around n plus 1 by the associative law. And that's it. As you can see, we have shown that a to the power of m times a to the power of n plus 1 is equal to a to the power of m plus n plus 1. So we have shown that this equality is true where instead of n, we have n plus 1. And so that was the whole goal of the induction step. So this completes the induction step. Because we've completed both the base case and the induction step, this closes the induction. So by mathematical induction, we have proven for all non-negative integers n, a to the power of m times a to the power of n is equal to a to the power of m plus n. And we have proven that this statement is true, given an arbitrary non-negative integer m. So really, we have proven for all non-negative integers m and n, this equality is true. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.